Hi everyone, welcome to the ICTS String seminar. So today we have Abhijit Gadde from TIFR who will be talking to you about classification of probe measures of multipartite entanglement.
Thank you very much for inviting me to ICTS. It's been a long time since I last visited, so it's a very nice feeling to visit again. So today I'll be talking about a special class of multipartite entanglement measures and their classification. In particular, the class that I'll be interested in is the one that is useful from a holographic point of view. A class of measures that you can calculate for holographic states in a simple way. So what do I mean by that? Well, so this I can clarify using something that we already know, namely measures of bipartite entanglement. So when we have a state, a bipartite pure state, a state that is defined on tensor product of two Hilbert spaces, we can define a number of quantities which capture entanglement between the two parties associated to a given state, and those are Renyi entropies, which you can calculate by, let's say, tracing over one party, constructing the density matrix, and taking trace of powers of density matrices. And a particularly nice measure in this class is the so-called von Neumann entropy, which is a derivative of this quantity near n equal to 1. So these measures, one understands how to compute them holographically for holographic theories. So, you know, so we know that the von Neumann entropy in holographic theories is calculated by the Ryuta-Kanagi formula given by the area of the minimal surface. There is a similar formula also for the Renyi entropies, although it is not as nice. It is given by a gravitational action in the presence of a heavy brane, a brane whose tension is proportional to 1 over g Newton, so it back reacts in the geometry. And the proportionality constant turns out to be proportional. It turns out to be proportional to n minus 1. So as n goes to 1, this tension becomes vanishingly small, and you can work in a limit where this probe brane does not back react on the geometry, and this brane does not back react on the geometry, and hence can be calculated purely in the probe limit. So it is this probe property that I will be interested in. I will be interested in defining those multipartite measures which can be computed by a probe calculation in the dual geometry. Okay, and I will try to argue. I try to move towards a classification of such measures. As you can imagine, a lot of the techniques used would be inspired by the work of Leukowitz and Maldacena, who essentially derived the Ryuta-Kanagi formula using gravitational path integral.
Sorry, just
yeah.
What does it mean to classify?
Yeah.
Like an exhaustively.
Yeah. So I will not go towards an exhaustive classification, but will outline a framework in which this classification can be done.
So will that classification be in the nature of some kind of a basis of linearly independent measure?
Yeah, you could say that. You could say that. Yeah, a ring. Let's say a basis of ring of measures, which you can multiply or add to get measures of similar type.
So Renyi entropy, you said a heavy. Does that count as a probe?
No, that will not be a probe. That would be something that would back react on the geometry. So I would be interested in getting measures which are computed by some geometrical quantity in the existing dual geometry.
Can I just generalize it? Is there any quantity that can be computed without any probe whatsoever, just like universal multipartite?
You can. So depends on what you call multipartite entanglement. I mean, you can take sums and differences of entanglement entropies. Sometimes that is thought of as some sort of a measure of multipartite entanglement. But there are cases, for example, you can come up with states for which the entire set of density matrices are isospectral. All density matrices that you can construct are isospectral. So no bipartite measure can distinguish between such states. And for those states, you would have to resort to something that I would call genuinely multipartite to distinguish them. So in that sense, yeah, it's really up to you whether you want to consider sums and differences of One.
Assumption differences, as you said, without going to isospect.
Yeah.
They are really measures of pixels, right? Not of, as you said, multipartite entanglement.
Yeah.
So maybe this one idea. What you look at here is not really distance to nearest separable state.
No. Okay, so let me comment on that. So what Surat is getting at is what people, yeah, exactly. So the word, measure rather than even multipartite entanglement is a loaded word. In quantum information literature, the measure is really justifiably used for a quantity that measures the entanglement. In particular, if you do a procedure which you expect should result in reduction, then the measure should also reduce. And this process is sometimes called LOCC, local operation and classical communication. And under such operations, you expect that any type of entanglement, multipartite, bipartite, any sort of entanglement should reduce. So you could insist that the quantity that you are interested in should have this property for it to be called a measure. And it is certainly a requirement that quantum information theory would impose on such a quantity, but we would work in a slightly broader definition of the measure. We will consider all quantities that are invariant under local unitary operations as measures of multipartite entanglement, because already so the motivation here is to look for measures that are nice from a holographic point of view. And once you have such a class, then you might want to search in that class if there exists a measure which is also LOCC monotone.
Actually, apart from LOCC monotonic, I also wanted that for a separable state.
Yeah, this is part of LOCC monotone. You can show that it is, yeah, because for separable states, LOCC is a reversible operation. So it is constant, and then you can change the origin to 0. So yeah, exactly. So you could choose to impose this condition, but it turns out to be this condition that it should be nice from a holographic point of view turns out already to be a stringent one. So I'm not going to consider that condition in the program of classifying probe measures. So what I will mean by measures are the quantities associated to a state that are invariant under local unitary transformations. So let's consider some state psi. So I will just say how I want to think about these quantities. So this state, let's say, is given as in some basis as some wave function where alpha are some orthonormal basis in so this is the basis of Hilbert space 1, and this is the basis of Hilbert space Q. So this is really a general state on a Q-partite system. So as I said, the quantities that I'm interested in are invariants of local unitary transformations. So you can construct those by contracting indices. So you can have psi and its conjugate psi bar, and you can contract indices to form invariants. And all indices of every party have to be contracted. Now, if you just take psi and psi bar and do that, then you would produce the norm, which you can normalize to 1. So in order to get a non-trivial measure, then you would have to consider multiple copies of psi and psi bar and contract their indices. One way to represent this contraction of indices is using some graphical notation. So you can think of psi as object of this kind, let's say. So this is my picture for a tripartite psi, where this, let's say, corresponds to party 1, party 2, and this is party 3. And I can take multiple such psis and similarly psi bars. So that can distinguish from psi by arrows. Yes, I will do that. Let me just do this and then. So I just have 3 copies of psi and 3 copies of psi bars. And then in order to contract indices, I simply draw lines from this outgoing arrow to the incoming arrow for each party. So party 1, for example, this I can contract with either this index, or this index. So this is really up to me. And for this guy also, I can make a choice. So in doing so, what I'm basically doing is permuting party 1 indices to the party 1 indices of psi bar. And that is given by some sort of permutation element which belongs in Sn, where n is the number of psi or psi bars, also called replicas in this measure. Similarly, I would also have to specify how the second party's indices are getting contracted, and that would be specified by permutation elements like so. So all in all, a general measure, again, by that I mean invariant under local unitary transformations, would be specified by specifying Q tuple of permutation elements of Sn, where n is the number of replica. Okay. No. In this example, I have chosen to be them to be the same. Yes, they are not related at all. The system is tripartite, yeah, because there are 3 types of lines, and n is equal to 3 because there are 3 copies of psi and 3 copies of psi bars. Q is the number of parties. Alpha 1 is the basis of first, alpha 2 is the basis of the second.
What tells your dimension of each?
That is implicit. I have not made that explicit. Q is the number of parties. Q is the number of parties. So that's why a given psi has Q types of lines coming out of it, because there are Q types of indices. And n is just that how many psis and psi bars you are taking to construct this measure.
Can in principle construct with an arbitrary.
Yeah, arbitrary number.
What exactly is the meaning of arbitrary number of sites? Is it the same state or different?
Same state. Same state.
I think like the Renyi entropy will have
N.
Renyi entropy will
N size. Yeah, n. Some n of Renyi. N size and psi bars.
What is its homogeneity in size?
Homogeneity in psi is n. Exactly. Homogeneity of the measure in psi is n. That I'm calling n. Well, von Neumann entropy, you don't construct this way. You have to do this, analytic continuation, all that. But let's first look at Renyi entropies, Renyi type measures, let's say. Because as I said, how else would you construct invariants of local unitary transformations? Just by contracting indices. Okay, for any n, and then you can try to take n to infinity, some with particular set of coefficients. For any case, we know that such a thing, there is a way to write entanglement, von Neumann entropies in terms of all the Renyi entropies also.
You suppose maybe some equivalent of like a single trace or something. I mean,
some connectedness.
Connectedness.
Yeah, exactly. That would mean the graph that results from such a contraction should be connected, right?
Need not be the same for each.
No, need not be.
So maybe connected in
Yeah.
some,
The other thing, it just shouldn't be
Disconnected.
to each independent
Yeah.
graphs.
like to disconnect this kind of all the contractions.
Yeah, once you look at all the contractions, it should not be disconnected. Individually, there could be disconnections. That's fine. Yeah, exactly.
So then it be straight slope the end.
Yeah.
Then how are we getting a road? This is a pure state.
Yeah, I will just say. Now, just to comment on what you said, Naveen, if you take 2 permutation elements to be the same, that means, let's say the solid line and the wiggly line, they always go together, right? So you might as well think of them as one party. This measure will not distinguish between the 2 parties because you're treating that the solid party and the wiggly party as a single party. Okay, so yeah, exactly. Okay, so this is some, this discussion was to just generally say how I want to think about general measures, general local unitary invariants in terms of permutation elements. Okay, now the map between permutation elements and the measure is not one-to-one. It is true that such a graph will give you a set of permutation elements, but it's not a unique presentation of a measure. That is because there is a freedom of labeling, relabeling these size. So you can relabel size. So you can move this here, this here. So that would correspond to a left multiplication on this set by some permutation element. And if you move around psi bars, that would correspond to a right multiplication on this set. So the number of measures you would have to mod out by such relabeling freedom. Okay. So using this relabeling, let me address your point. What you can do is you can set the first guy to be 1. That's obvious because if these solid lines are connected like that, let me just take this guy, put it here, take this guy, put it here, so that this always becomes 1. And then the rest of the lines do whatever they do. In fact, if you do this to be 1, that means you are left multiplying, let's say, by sigma 1 inverse. Then all these things, sigma 2 will go to sigma 1 inverse sigma 2 and all that. So in this sense, sigma 1 will go to 1 and the other elements will go like this, right? So you can gauge fix, some of the freedom that you had by setting this sigma 1 to 1, let's say. Okay, but this also has some nice interpretation because if you look at this, one of the elements that would be involved, one of the units that would be involved in this construction, once you set this to 1, I can just think of that unit as this because I've already contracted the solid line. So what I have is psi alpha 1, alpha 2, alpha 3, psi bar, alpha 1, beta 2, beta 3, sum over alpha 1. This is also sometimes called the density matrix, alpha 2, alpha 3, beta 2, beta 3. So this would be the density matrix on the remaining 2 parties. Okay, so you can think of this as simply some sort of a vertex with 2 fundamental, one fundamental, one anti-fundamental index of party 2, and one anti-fundamental, one fundamental index of party 1. Sorry, party 3, let's say. So it is just the same, right? Because this object also has two outgoing arrows of this sort and 2 incoming arrows of this sort. So I'm just relabeling this particular contraction with party 1 index as a density matrix on the remaining parts. The ordering doesn't matter as long as you keep track of the arrows, which is fundamental one, which is anti-fundamental.
Why is that the solid lines, the wiggly lines always?
No, they do not. I'm saying in case they do, then that means that you are treating this party and this party as the same party. You're not distinguishing between them. Okay. Okay, so so for a density matrix also you can think about it this way.
There are few types of solid and wiggly.
Yeah, and the dotted line. All the lines are Q. Yeah, the arrows.
So there are 2 types of wiggly lines.
No, sorry. Q types of wiggly lines. No. Q types of lines. One type is wiggly, one type is solid, one type is dotted like that. Yeah, and how many wiggly lines? N types. N wiggly lines are there. Each line is N times.
N types of
each line, yeah. N times each type of line. Yeah, exactly. Okay. So in general, one can think about these invariants in this way, which once you set sigma 1 equal to 1, can think about contractions of density matrices, density matrix indices also. Okay. Now, such a measure sometimes has a symmetry in some special cases. And the symmetry is exactly the commutant of all these elements. Let's say all these elements, sigma 1 to sigma n, generate some subgroup K of Sn. Then the commutant.
This is contracting with delta function.
Yeah.
Can you also use an epsilon tensor?
Can you use, so that becomes now dimension specific. right? So no, I'm not going to look at epsilon tensor contractions, but you could, I think you could. Because mainly we are interested in applications of these to holographic theories, in particular quantum field theories, which will have infinite dimension. So you can look at the subgroup of these subgroup generated by these sigmas in Sn. Let's call it K. So all the elements in Sn that commute with K would form a symmetry of this graph. Okay. So before that, let me just to familiarize, go to a bipartite example. Just to kind of go to a more familiar case. So there we talk about the Renyi entropies as trace rho to the n. So in this case, you would graphically denote it like so. So you would have a bipartite state to begin with. So let's say it's a state of this type. So I'm taking n copies of size, and then let's say I contract the party 1 index. This gives me the density matrix rho alpha 1 beta 1. Okay, and then trace rho to the n simply contracts this index with the next guy, this guy, the next guy, and so on. So this becomes contraction of this type. This goes here, this goes here, this goes here, this goes here, and then finally comes back. So it's this. Okay, so you can think of the Renyi entropy in the graphical notation as this, or in terms of just the density matrices, you can think of them as here. The solid line will not be visible because I have kind of compressed it in this node, and then there is a periodic boundary condition, so that you come back to this same point back. So this would be trace rho cube, but in general, if you have n of these, then that we trace rho to the n. Okay. Okay. So as I was saying, there is a particular symmetry of this measure. So in this case, for example, one can talk about the symmetry. Here the elements involved are sigma 1, which is 1, and sigma 2, which is G, which is the generator of Zn in Sn. Okay, so if you look at the commutant of Zn in Sn is again Zn, the same Zn. So that's why this measure has Zn symmetry, and that is just clear because you get a circular graph which you can rotate and get to the same graph. So it's really the symmetry of the graph that you get. Okay. So this symmetry we sometimes call the replica symmetry of the measure. Okay, so let me borrow the terminology and call the commutant of K inside Sn the replica symmetry of this measure. Okay.
You wanted to have something like relative entropy.
Yes.
Is that, of course, that also has logs, so you have to do some calculation, but is there a way to obtain that from this kind of with two different density matrices?
Right.
That's also bipartite, right?
Yeah, that's bipartite. Yes, you could construct a multipartite version, not perhaps of the relative entropy because it has this log, etc. But you can consider some Renyi relative entropy, things of that type. But maybe if you allow for some analytic continuation, you can also define some analog of relative entropy. But you know, all the nice properties that the relative entropy has, I don't know whether.
Yeah, no, I was also just trying to think. So in those cases, how are you going? Because there you talk of two intervals or two regions, A and B, and then there is the complementing.
Yeah, so that would be, you know, you have a rho, a density. So in order to define relative entropy, we just need a rho and a sigma, right? Defined on the same system. So you just have a bipartite, pure bipartite system. Let's say instead of talking about rho, let me talk about a bipartite pure state, which after tracing over one, you get rho, let's say. And then there could be another pure state which gives sigma, and then.
But you don't even
General density matrix.
But it's with a single system.
Yeah, it's a measure of distance. Relative entropy is really to think of as
So it's not like two different regions.
No.
yeah, for the same system.
Yeah.
Have a,
Yeah.
and
Yeah. It just as Suraj said, it's really the statement about how different one
So,
density
but
matrix is.
that, here you're looking at only
A given state. A given state.
And
Yeah.
then, so you can't talk
Yeah.
about things like this.
That's right. There may be a way to do that, but I don't know. For now, I just want to look at.
Actually, relative entropy doesn't have a rule of bulk relative entropy is boundary relative. You just measure the bulk relative entropy, the bulk QFP. There's no geometry. It doesn't have a G.
What you wait for is probably the mutual entropy.
Mutual information.
Yeah.
Mutual
That
information.
will be something which will require like
Tripartite.
Tripartite.
Right. I mean, you can talk about mutual information for density matrices also, but then you need density matrix on two parties, or in other words, a pure state of three parties. Yeah. But that also is a relative entropy of some sort, right? Between row AB and between row A tensor row B.
Fully separate. But that's also not holographic. That separated state has a file.
Yeah.
It's a disentanglement.
Yeah. I mean, I would say, separate, but okay, it's a different word, right? I mean, separable state is a bit different. Product state. Yes, exactly. Yes. Row AB and row A tensor row B. Yeah.
No, I was not so much interested at the moment on the holographic side.
Yeah.
It seemed to be.
Yeah.
I just want to see how
Sure.
any of these other measures one cares of would fit into your
Yeah.
classification or your scheme.
Right. So
would those things mutual information also kind of?
So I can say mutual. Well, I was going to say about relative entropy, which is one case of the mutual information. No, I was just going to say that there is a thing called Renyi relative entropy, which is rho to the power alpha sigma to the power 1 minus alpha, something like that. In the alpha going to one limit, you get rho log sigma, this kind of thing. So there is a way to do that in the replica as a replica trick. So basically producing logs would be difficult. They would have to be done through some analytic continuation. So,
but otherwise, you're saying that modulo also some finite dimensional inverse space cases, all other these things fit into the scheme.
Yeah, exactly.
Assuming it has a power series,
rho. Yeah, exactly. This is very general. It encompasses all those cases.
All these diagrams can be distinguished if it's a probe or a.
Yeah, so that's what I will talk about. So precisely, I will be interested in obtaining conditions on these permutation elements so that the measure given by these would lead to a probe measure. The replica symmetry is the commutant of all these permutation elements inside the permutation group Sn. At the level of these graphs, those would be the symmetries of the graph, automorphisms of the graph. Yeah.
Sorry, but these symmetry elements are all the contractions with.
Yeah. No, LOCC. No. So at the beginning, I said I don't want to talk about LOCC. Okay, I just want to construct local unitary invariant measures. So these sigma 1, sigma 2, sigma 3 is just the way. They're just specifying how I'm contracting party 1 indices. They are contracted with the action of sigma 1. Party 2 indices are contracted with the action of sigma 2, and so on. So they just specify how the indices are contracted from the set of size to set of psi bars. Just that.
Replica symmetry can be non-abelian.
It could be non-abelian also. Yeah, exactly. But I will be interested. I will first. In this work, basically, we focused on the case of abelian replica symmetry. So I will just focus on that case. But in principle, one can try to generalize this to non-abelian replica symmetry also. Okay. Yeah. Yeah. You could have. Yeah, sure. Exactly. Yeah. I'm just calling this commutant of this as. Okay.
So sigma 1 to sigma
Q.
one element of one measure.
There are Q elements. This one is a permutation element. This one is a permutation element. There are Q elements. Each one tells you how eighth element here tells you how the indices of party A are contracted. Okay. So it's a tuple, a Q tuple of permutation elements that specifies the measure. Okay.
There's one state and
Yeah.
you have two states or something. This invariance is still
Invariance. One side to side. Yeah, you could sprinkle different states also. Yeah. I mean, it would go towards constructing measures, that kind of measures that Rajesh wanted, of multiple states, trying to measure differences, distances between the states, and so on. One can try to do that. But for now, I just interested in the single state, because at the end of the day, I will be interested in, let's say there is some CFT, large central charge, large gap, holographic CFT. There's some vacuum state or any other state, and let's say you give me some regions, Q regions, and ask, what is, so we want to construct some quantity that measures the entanglement, the multipartite entanglement in these regions, and that can be computed by some nice geometric object on the dual side. Okay.
So far, the dimension of the Hilbert space
Hasn't entered, yeah.
But presumably, when you distinguish between probe and maybe that will be important, right? It's only in the large dimension limit that you can distinguish.
Yeah. So in order to discuss probe measures, I would have to go actually to a holographic setup. There I have to discuss the construction of those measures. So they would not enter so much into the dimension, but actually change the setup into replica trick in quantum field theory. I should say, well, one place where the dimensions does enter is that if the dimensions, all dimensions are finite, the information that is locally that is invariant under local unitary is some finite information, right? The space of such things should be finite. So even though you get these invariants, the ring will not be freely generated. There will be relations, and that would come, there will be relations of relations. So in general, the structure of this ring is going to be very complicated, unlike the ring of matrices here, where if you have, let's say, some d-dimensional row, then pretty much you have a row to the d independent information, row to the one, row to the d. I mean, the first d entropies would be the independent information. The rest of it you can explicitly write in terms of this using this Cayley theorem, right? It gives you the relation between higher powers of matrices. But here, because these are tensors, explicitly writing those relations would be very difficult. But nevertheless, you can characterize this ring in some way. So in that sense, if in the finite dimensional case, even though there are infinitely many measures, they would be truncated.
I was going to ask, even if you take a holographic CFT, at this stage, can you tell us the measure of
well, I will find the quantities which have such a characterization. That's what I'll do. So exactly, this is so far very general, but I will find conditions on these things so that measure would then be computed from a bulk point of view in a probe fashion.
Just maybe a stupid question, but if it is a dimensional limit, as you said, then you don't have any relations.
Yeah.
Then why can't we consider inverses of rho and so on, like negative powers of the density matrix? Something.
No, but inverse is some bigger unitary idea, right? So here you want to do this for a general q-partite state, right? Let's say, so that's why I like to think in terms of size rather than psi-bars, because when you start thinking about row, that's really well suited for a bipartite case where you trace out one and then you have a row on single party and then you can play with it, right? But here you have a psi which is on q parties. Nevertheless, let's say you can talk about a row, which is by tracing out one party like this. So you would have a q minus one things left, but inverting would mix all these indices, won't they?
For pure state, of course, but here in general, you will probably be interested in, and you could restrict to the class of.
Yeah, but even in the limit where some eigenvalues become very small, we can just that. And it's not pure, but some eigenvalues. In quantum field theory, for instance, some of the eigenvalues are always becoming very small.
Basically, I don't know how to define inverse of a tensor. Right. So as a matrix, you can do it, right? But what does it mean? What is it? Okay.
Anyway, yeah, maybe it's not so, but I was thinking.
Yeah, there is some eigenvalue equation that one can write down, some tensor eigenvalue equation, which has the property that those quantities that you obtain, the eigenvalues are invariant under local unitary transformations. Okay, that I know, but more than that, to go towards inverse, I don't know.
Yeah, I mean, to address inverse, not necessarily to consider 1 over rho plus a, and let a be something, a complex number, and then you don't.
Yeah, go to the n by e. We end up looking at that kind of string.
Then you have to, yeah, it depends on the semantic continuation, something here. Singular equals 0.
Yeah.
If modifier is smaller than 1, you would again worry about that.
Exactly. So that
you want
but you
modifier
could have some,
then yeah.
but you might be able to. It's
No, but maybe yeah, I don't quite know. Maybe I'll talk to you about what is known about these higher dimensions.
I don't know myself much about it.
Okay, I see. Okay, good. Fine. So as I said, I'm interested in computing these measures in holographic holographic conformal field theories, and then that and insist that they be given by some probe quantities. So let's look at, sorry. Okay, good, thanks. Will it stop automatically? So much lag. Okay. Fine. So now let's consider these measures in quantum field theories. The nice thing about them is that the way we have defined them, they directly are amenable to a replica trick in quantum field theory, right? Because we are basically defining them by contracting indices, which in quantum field theory would amount to gluing of regions. So let's, for convenience, take the case of 2D, so that I can draw pictures. Let's consider some vacuum state or any other state and a bunch of regions. And this, after a Euclidean path integral, would produce a wave function psi. And the psi bar would be produced similarly on the northern hemisphere. So this replica trick essentially means that you take many copies of these objects and the way you are instructed to contract indices, you glue the regions together. So you will have region 1, region 2, region 3, let's say, and let's say that you impose, you take sigma 1 to be identity, so then you glue this to this. And then region 2 could glue to a region 2 here and 2 here. So at the end of the day, when you are done with all the gluing, you will end up with a sphere with 3 ramification points or branch points, if you wish. And as you do monodromies around those branch points, you will end up on various sheets. The total number of sheets in question would be n, the number of replicas that we use to construct such measure. So that's why this labeling of the measure using permutation elements maps nicely to a replica trick. Less than n. Not less than n, less than equal to n. Yeah. Because there could be a big cycle also.
Sigmas themselves matter, right? It's not like the conjugacy class.
Good. Yes, so indeed, the details of sigma do matter, not just conjugacy class, but you can put a simplifying condition on the sigmas so that the probe condition just can be characterized in terms of the conjugacy class, as I will show. Okay. Unfolded picture. Yeah, so we would have to do this using the gravitational description, and we'll follow the methods of Leukowitz and Maldacena. So just to remind you the way they did it for bipartite case, right? So let's consider computation of trace rho square. Okay, just the bipartite case. So there you would have a sphere with a cut, that would be the density matrix rho, and a sphere with a cut, the same sphere with a cut, and then you glue this one to this one, this one to this one. That's how you would construct a replicated manifold, which would be a sphere with this two double cover. Yeah, exactly. So what Leukowitz and Maldacena do is that they look, first of all, they take this, and as Suraj said, it is better to unfold this and look at the manifold that results from gluing. So in this case, that would be again a sphere, right? But with two special points. Those points are special because those points, they came from here, and the angle around these 2 points is 4 pi. So there are points with conical axis 4 pi, conical angle 4 pi. And then, so in general though, you could have had a higher genus Riemann surface also, depending on how many cuts you consider, how many intervals are there, let's say in party 1, you would obtain a higher genus surface. But in this simple case, I'm just looking at a single interval. So once you replicate, you get a, so let's call the manifold on which you started as M1, let's say, and then after replication, you get M2. Okay, if you had n replica, then you would get Mn. Okay, and now what they do is they consider a gravitational solution whose boundary is this M2. 2 pi n. 2 pi n, yeah. Conical axis meaning conical angle, the full angle, yeah. But again, the topology is that of a sphere with 2 conical points. So the gravitational solution that fills out this M2, let that be B2. Okay. So at this point, they make an important assumption that the replica symmetry of the measure, which this manifold M2 certainly enjoys, is also enjoyed by this bulk B2. This is the statement sometimes called the replica symmetry is unbroken in the bulk. Okay. And once you make this assumption, which we will also make, you can orbifold this whole geometry by the replica symmetry. Yes, it does turn out to subtle. In fact, in this case, this will be subtle. I'll make some remarks on that later. Even in the bipartite case, this sometimes turns out to be subtle. So you mod this out by, in this case, the replica symmetry is Z2 to get a manifold, which we'll call B2 tilde. Now, what is the boundary of B2 tilde? Well, the boundary of B2 tilde is again M. This is the manifold that you started off with, because this gluing procedure replicated this manifold to M2, but after the orbifolding by the replica group, this M2 became again M. Now, what became of B2? It became B2 tilde, and we will talk about what that B2 tilde is momentarily, but for now, we'll just focus on this particular feature of their procedure. Namely, you construct this replicated boundary manifold Mn, and you mod out by the replica symmetry group to construct a manifold which ends up being M. So if you want really the measures that are probe measures of the original geometry, the boundary that you get better be the boundary that you started off with. So this is the property that I will require in general. M1, yes, exactly. So I will require that orbifolding replicated boundary by a subgroup of replica symmetry gives original boundary. Sometimes you may have some excess symmetry that you don't want to orbifold by. It's possible. But in any case, this is a more general condition, right? No, as you said, right, in the case of N even, there will be a Z2 also. Yeah. You just do the modding out by Zn. Because in the even case, and the even case, you also have a Z2, right, which makes it into a dihedral group. Actually, I'm not sure about the dihedral group because of the arrows. Sorry, Loga. Yeah. Yes. I will say all that. Yeah. So what this means is that this subgroup H has to act freely and transitively on a replica set. Right? Then when you orbifold by it, you will get a single copy of M. So now this can be phrased in terms of these sigmas that we had. So we had these sigmas which labeled a measure, labeled a particular measure. And H, as I said, is some replica symmetry group is the commutant of that. And now that the commutant should be such that it should act freely and transitively on the replica set. So now we can characterize. H is a subgroup of commutant. Okay. So now we can characterize what kind of measures will have this property. So first of all, as Rajesh said, it is sorry. No, there should just be some H which acts on that free and transitive way, which when you orbifold will give you back M, right? If it acts.
H acts, the whole replica symmetry will also act.
If H acts freely? Yes.
Then that should be true for
the full replica symmetry. The full replica symmetry? No, not necessarily. I will give you an example where this is not true.
So if the commutant is abelian, then H is the full.
That even is not the case sometimes.
Even then, it's cyclic, for example, then
Yeah.
H is not the full.
No, then H is the full group. Yes. Let me proceed a little bit, and then I think I will do some example also. That will make it clear. So, as I said, it has to act freely and transitively on the replica set. And now at this stage, H could be anything, abelian, non-abelian, but I'm going to choose it to be abelian, so that it cannot be folded by an abelian group. Now, H is some subgroup of Sn, right, which acts on these n things in a free and transitive way. So then there is a theorem that says that H, first of all, in fact, if you just require H to be transitively acting on that, then it implies that it acts freely also. So you don't have to impose this condition. And furthermore, it says that H is maximal, meaning H is its own commutant. Okay. So now if you want to choose sigma so that their commutant has a subgroup that is H, you need to simply choose them from H. That's it. So you just choose sigma i's. Yeah. So the important property I'm using is that H is its own commutant. If you want to look for elements which commutes with H, they only live in H, nowhere outside, right? And what were sigmas? Sigmas in particular commuted with H. Yeah. No, sorry, commutant of the commutant.
Isn't that what you're using? Because this was the original sigma, since commutant was your H.
So
isn't that because you're using the commutant of this H's, and now you're talking of the commutant of.
So let me just say the following. So K is the subgroup of the thing that is generated.
K is the commutant.
No, K is the
subgroup.
no is the group that is generated by.
Then you look at
its commutant. So so this guy, exactly. So this guy is the replica symmetry C of K, commutant of K, right? So this guy H is some subgroup of that, right? Now this means that you can put commutant on both sides and reverse the. Nobody have to reverse this thing. So C of H is inside. Okay, fine. Commutant of commutant. Yeah, exactly. So, and then this is equal to H. What did I do? I do it wrong. That's a theorem. Yeah, I mean a transitive subgroup that a subgroup that acts transitively, an abelian subgroup that acts transitively on a cell. Okay. Yes. Sorry, this I got it wrong somehow. I got it backwards. Well, I mean, as I said, we don't really need to think in this fashion. The simple observation is the following: if this H is taken to be abelian, then we know with this condition, it means that the elements that commute with H, in particular these sigmas, were the elements that commute with H. They have to live in H itself. That's the only thing that I'm using. Okay. If the commutant of H were bigger than H, then I would have missed some sigmas, right? But now I'm not missing those because of this theorem. It says that if I want to pick the elements that commute with sigmas, commute with H, they have to be part of H itself. So that means if I want to consider some measure which has this property, I simply need to pick sigmas from H, some abelian group. But because now I'm not even specifying what this abelian group is. So you can You can.
Sigmas are automatically abelian.
Yes, exactly.
generating
Exactly. So what this does, so this condition basically translates to saying sigma i's are mutually commuting. That's it. Yeah, I'm chosen in the sense I put the condition that the H is abelian. H is abelian, yeah.
Maybe I'll just repeat what you said to make sure I
Yeah.
understood. So the statement is that you start with essay.
Yeah.
Then the first thing you do is you try to find a abelian subgroup of essay.
Yeah.
Which acts transitively on essay.
No. It's the commutant of the. It's the replica symmetry of the.
For starting from this stage, yes, exactly. So there's some H, which is some subgroup of replica symmetry, and this has the property that it acts transitively on n objects.
Yeah. So there's a consideration. So I just take H, and then set a H, and then I say that if I can choose some sigmas from those H.
Yeah.
Okay. They will also of course commute because H is abelian. And you are saying that so corresponding to that sigma. Corresponding replica symmetry is the thing that commutes with the sigma.
Yeah.
Would be also in H.
Would be bigger than H, but H would certainly be in that as required. Yeah, you could have said that. Yes.
So
Yeah.
if you just take sigma and mutually commuting.
Yeah.
Does that uniquely depend on H?
Yeah.
Because then I can definitely construct things which commute.
Yeah. In fact, H then becomes K.
It then becomes K.
Right.
K is the thing that's generated by sigma.
Sigma is, yeah.
So if it, okay. So if you start with some mutually commuting sigma,
yeah.
Okay, and then I just take the full all the generated by the sigma.
Yeah.
And all the.
Exactly.
And then I model by the.
Yeah. Exactly. Exactly. Yeah, but I tried to be general. Yeah. I did not really want it. I just wanted to characterize, these measures K with abelian replica symmetry. So that's something that I can use mod out, some abelian group with which I can mod out. That was the condition. Yeah. Right. The subgroup of it is K. Yeah.
And K is also the group that the sigma can.
Well, I mean, you could have, for example, Yeah, exactly. Yeah, exactly. Okay. Fine. So now I have this H. So sigma is should be mutually commuting. So let's give some examples of such things. So clearly the any entropies are of that type where sigma 1 just bipartite case q is equal to 2. So there sigma 1 is equal to 1 and sigma 2 is equal to Zn. And indeed, you can see the replica symmetry group is also the one that is generated by this, which is Zn. Sorry, G, the generator G. This sigma 2 is G, which is generator of some Zn. Okay. And the replica symmetry group is basically Zn. Now there's sometimes people use these entanglement negativity. You can characterize this entanglement negativity also in this way. So they construct this thing in terms of some replica trick again. So this is defined for q equal to 3, and this is sigma 1 is equal to 1, sigma 2 is equal to G. Again, the generator some Zn, and sigma 3 is equal to G inverse. Even these are mutually commuting generators. So exactly. So this in principle makes everything clear, right?
Right. In an abstract.
Okay. Okay, fine. So I will just do the following. Yeah. So let's say the Renyi entropy was this, right? Right, and then the negativity is just the opposite. Right, and this goes oppositely. Well, another, okay, sometimes. No, but it's basically this. It's not very far from this. It's what is called the use partial transpose. So you use rho, alpha 1, beta 1. Those are party 1 indices. Rho alpha 2, beta 2. Those are party 2 indices. And you do its partial transpose. Let's say on the second index. So rho beta 1, alpha 1, and here you write alpha 2 and beta 1. Beta 2, and then once you do this rho partial transpose, you take nth power of it, nth power and trace. But this is the same one, right? Just these indices flow oppositely. The nice thing, there is some nice thing about this quantity because there is this theorem by someone, I forget, that which says that you can use, I always get this, positivity of the partial transpose as a test of separability. So now I would have to say what separability is also, but this goes towards this LOCC business. So these measures somehow have nice properties in characterizing separable states. Yeah, right. Exactly. So if you see that there is a negative eigenvalue for this, that means the state is not separable for sure. Okay, fine. Okay, so we have this, at least some condition on these sigmas, which have the property that has a replica symmetry, a subgroup of replica symmetry, which after modding out will produce me the same manifold M1 back as I needed. Now I have to look at the bulk and see how I can get towards the probe measure. So for that, let's again go back to the Lipkowitz-Maldacena construction and see what happens in the bulk. G1 inverse. Here, right? These, yeah. So that's the kind of thing we will encounter. Exactly. I will show that.
So Zn is the H.
Yeah. Exactly.
So because you take the G's and G generates full Zn.
Yeah.
You add G inverse, doesn't do anything.
Doesn't do anything.
Still
exactly.
generates Zn.
Which is K also. Yeah, as we said. So I was wondering, Ashok, your question that whether this H has to be replica, H has to be the replica symmetry or a subgroup of replica symmetry, right? That's what you're asking. But I mean, in general, you could have some bigger symmetry, right? So let's say, especially in the case of disconnected graphs, there could be some extra SN type symmetry, right? Permuting those disconnected graphs. So I'm removing that possibility also. Okay, so Zn times Z2 coming from 2 and 3. No, you don't want to change the role of 2 and 3 though. I mean, it should just be the symmetry of the graph, not up to relabeling of edges. Okay. Fine. So now let's look at the bulk more closely and see how exactly we get to the probe measure. So this is at the 0th level condition that we wanted to get back the same geometry, so the boundary at least be the same. But now we also want the measure should be a probe measure. So in the case of bipartite entropy, as we said, this M that you obtain from by orbifolding Mn by Zn again gives you M, as we discussed. So inside you have B tilde n, which you obtain by orbifolding Bn by Zn. So Bn, if you remember, was again a sphere with some conical excess angles, and you had some bulk solution, smooth bulk solution that fills in that sphere. So when you orbifold by Zn, so in that before orbifolding, this Bn was a smooth solution, as I said, and in that bulk you can identify a locus that is fixed under the action of Zn, and that it should exist is clear from the fact that there were 2 points on the boundary which were fixed under the action of Zn, and the locus emanates from those and ends up in the other point. Okay, and then when you orbifold by Zn, that locus, nearby that locus, you get a conical singularity, a conical orbifold singularity. So the conical angle here becomes 2 pi by n. Okay, and moreover, now at this stage, so this would be the dual to the Renyi entropies, but and so you use the fact that such a conical singularity is also appears when you have some sort of a brane whose tension goes like 1 over g Newton times n minus 1, engineers a conical singularity of this type, and so it back reacts in the geometry, and this quantity by itself is difficult to calculate. So from this point of view, it's clear that in the n going to 1 limit, this conical singularity flattens out, and this can be just calculated by a probe calculation, which is just the area of this minimal surface, which does not back react in the geometry. So this procedure requires you now to introduce some sort of n whose n going to 1 limit you want to take, right? So far we did not have that. We were considering some general measure, but now we will have to consider a family of measures labeled by n, which when n goes to 1 results in a singularity whose conical angle flattens out. Okay, so let's try to do that in the case of this Q equals 3 on S2. Okay, so there you have these 3 points, as we discussed, with some cuts. And what are these cuts exactly? Well, we can, so let me just take again n is equal to 2 so that it's easier to show. So there are 4 just a second. I should specify what exactly it is. No, we did not even do that here. Okay. So now let me consider a Q equal to 3 case, which is the following. So, and n equal to 4, and I will write down the explicit permutation elements. 1, so this is identity, and the other is the transposition, a pair of transpositions, 1, 2, 3, 4, and this one is 1, 3, 2, 4. Okay, so you can think of them as the following contraction of density matrices. Okay, so this is a particular contraction of density matrices. In terms of explicit permutation elements, it is given like so. Okay. Yeah, exactly. Yes, exactly. Yeah. Yes, exactly. And now we can look at the ramification in the sheets also. So you have 4 sheets. So in region 1, they look like this. 1, 2, 3, 4, because it's just identity. And in the other region, they look like this permutation. Region 2 and the region 3, they look like this one. So I'm doing this on in CFT2, let's say, with 3 regions. Right. So here I have sigma 1, sigma 2, and sigma 3. And I'm just showing the ramification structure on each region. Yes. Yes, exactly. And then you would also identify the conical singularity around each plane and impose that in some n going to 1 limit, that conical singularity should flatten out. Yeah. Yes. No. I mean, that's towards the classification, right? I mean, this is so far very general. And impose meaning, I'm trying to find conditions on sigma so that happens, right?
Okay. So
I will require that condition.
So you're saying that beyond n goes to 1, there are conditions?
No, just this condition that in the n going to 1 limit, this flattens out. Yeah, so that's what I'm getting towards. No, this is so far the boundary, but it is important to understand what is happening on the boundary so that we can see the locus of fixed points that extends into the bulk and what will happen when we orbifold by that. No. Yeah, exactly. So far this is, I'm just drawing M2 here associated to this case. Okay. So here the ramification is this. So first sheet goes here, second sheet goes here. Well, okay. M4, but M4, let's say, but my labeling is that it is going to be M2. This is a 2 by 2 lattice. N by N lattice will be Mn. Okay. It doesn't matter. It's something. It will become clear when we go to the classification. There it will turn out only these things matter. The Mn thing. That's why it makes sense to call them Mn. I will just say. So the ramification is like this. And then again it does, 1, 2, 3, 4, and that has to be like this, right? So you have in the region 1, you do this ramification to go to region 2, you do this ramification to region 3, and so on. So now the thing to note here is the number of fixed points. Okay. So when you unfold this thing, you will again get a sphere. Okay, just like in this case. Here also you got a sphere with 2 special points where you had conical axis. But here you are not going to get 2 special points, but rather 3 special points, the 1, 2, 3 that were there. But rather you will also get their copies. Okay, which is clear from here, right? Each ramification here is happening in 2 sets. There is 1 ramification point. So if you don't look at these points, this is just a disconnected ramification between 1, 2 sheet and 3, 4 sheet. So that has 2 points here. So you will get 6 points. So this would be 1, 1 prime. This another will be 2, 2 prime, and here will be a 3, 3 prime. So in the replicated manifold, you will get 6 special points. Okay. So in the bulk, you will have a locus of fixed points. So again, fixed under what? That's also important. So these 2 points were fixed under a particular Zn symmetry, Z2 symmetry. Okay. Yeah.
I guess here the group is Z2 cross Z2.
Yeah, Z2 cross Z2. One Z2 that does this vertical, and the other one does Z2 horizontal.
Generated by the
Yes, exactly. Exactly.
not Z4.
Z2 cross Z4. Z2, yeah. That justifies the labeling also, I guess. So now you have some locus which is fixed under locus of fixed points under one of the Z2s, which will emanate from 1 and 1 prime both. Okay, and then there will be another locus that will be invariant under the other Z2, which will emanate under 2 and 2 prime, emanate from 2 and 2 prime. And when these two loci meet, they have to meet on this locus, because these two loci were being permuted by the Z2 which kept these guys fixed. Right? That's the nature of this Z2. The Z2 that permutes these guys is the one that keeps these guys fixed. Right? So you will get this picture that when they merge, this has to happen where these guys merge. And moreover, when these two guys merge, from there must emanate another set of loci which go and meet 3 and 3 prime. So all in all, you get a picture like this of fixed points.
You should get basically 6.
No. So this is at the level of M2. Okay, we have not orbifolded yet. Okay, that's why we also have 6 points on the boundary. We want to get finally the boundary which looks like the same as before. But now, given that you have this particular structure of fixed point loci, you can mod this out by Z2 times Z2, the replica symmetry group. Now what will happen? Well, when you mod out by one of them, let's do it in steps. When you mod out by the Z2, which keeps these guys fixed, then you will get a conical deficit here. This angle will become pi. Angle around this locus will become pi. The angle around this will become pi. But this acts transitively on these. These guys, are permuted under this Z2. So this will be identified, and these two will be identified. So in this intermediate stage, when you orbifold by a single Z2, you will get two loci with angle pi, and these two separate loci, 2 and 3, because these guys get identified. I mean, 2 and 2 prime get identified, 3 and 3 prime get identified, but the conical angle around them is just 2 pi. Here also it's 2 pi. Okay. But now when you orbifold by the second Z2, that Z2 used to fix this one, and it acted transitively here. So that makes these two angles pi, conical angles pi, and it identifies these guys. So at the end of the day, when you get to the stage of B2 tilde, which is equal to B2 by Z2, you get this picture. Yes. In the bulk. So you have 3 points again, back to the 3 points. Here you had 6 points. When you unfolded the surface, you had 6 special points on the boundary. But after orbifolding, you again got back to 3 special points. And inside the bulk, you had these loci, which now became just multiple copies of loci, which now become single copy of locus. But now you have angle pi around each of them. Okay. Now you can try to do this for higher values of n. Now for higher values of n, when you start again exactly from this sort of setup, you have 3 regions, sigma 1, sigma 2, sigma 3, and you do this construction, but now you do an n by n grid. So you have Zn times Zn. One Zn permutes the rows, and the other Zn permutes the columns, right? So for the region 2 associate, the Zn that permutes the rows. For region 3, you associate the Zn that permutes the columns. Again, you can draw a similar picture. But now what is different in that case is that the manifold that you get is not a sphere. Okay, it's some higher genus surface. What is the genus of that surface? That can be calculated using Riemann-Hurwitz formula and so on. But it's some complicated beast. But the assumption that the bulk, that there exists a bulk that preserves the replica symmetry means that you should also find a particular set of fixed point loci in the bulk, and that locally should have the structure of the following. So you have, single point one will now get multiple copies, n copies namely, right? Because the other Zn will act transitively and make copies of that. Okay, because it's fixed only under one of the Zns. Okay, so this is the set of ones, and similarly there will be a set of twos, and similarly there will be a set of threes. And now from the bulk there will be these fixed point loci that shoot up.
This is the case where Zn cross Zn.
Yes. Q equal to 3 Zn cross Zn, yes. Exactly. And you will again do this similar type of Orbi folding. Orbi folding by one Zn, which fixes this, will give rise to a conical singularity, conical angle of 2 pi by n around each of them, because it is fixed under that Zn. But it will collapse this guy into a single guy, because that Zn permitted this. Okay. And then once you mod out by that Zn also, the one that you got here, which had an angle of 2 pi, will get 2 pi n, and this will identify all that. So at the end of the day, you will get a similar picture. Okay, where the angle here is 2 pi by n, 2 pi by n. Yeah. So what is the nature of the singularity? That's not quite clear. So this goes to the question of whether the replica symmetry in the bulk is really preserved or broken. So in this case, one can show that the replica symmetry is preserved in the case of n equal to 2. Okay, so there also you could have asked this question: what is the nature of the singularity? It turns out there is no singularity there.
Yeah, there was no. For 3 onwards.
Sorry, how do you see that there is no here?
For the bipartite.
No. In this tripartite, but n equal to 2. In this case,
For n equals.
where you do have this junction type object, it just came because you did the Orbi folding. In the previous picture, there was no singularity. Okay, so it could be that there is no singularity at this point.
I think of this as just, like some kind of singularity, just as some kind of strings with some variation.
Yeah.
Then, the question is, you're asking, I think, is what is the kind of name that you can put where you can all these things.
Yeah.
Like the variant operators.
Yeah. These are codimension 2. Yeah. Well, these are codimension 2. The lines even. Yeah. So this is a point which is a codimension 3 point.
You have this PQ string junctions.
These are kind of, you're saying they're not time. Yeah, this is just a line. Yeah, but that you can forget about the time. I was thinking that with intersecting soap.
In higher dimensions, that's what will happen. Exactly. It will look like soap films. In fact, in our first paper, we do call them soap films. Yeah.
But the question is that, the question is about some consistent curvature that these holonomies are all. This holographic limit, it doesn't matter. Your plane is anyway becoming integral. The intersect.
Yeah. So what exactly is happening is really related to the question how the solution looks like, and that is not easy to compute. Okay. Well, here it was smooth. Here this happened in a smooth way. I don't know. In general, I don't know what it is. And you know, we do some CFD checks of this, and there also you can check everything up to the OP coefficient. Is this 3-point thing? What can one check? Sorry. Yes. Yes. Yeah, you could do that. Yeah, exactly. Yeah, you can compute them certainly. This calculation can be done, but I don't know what the check with the check that you're talking. So, but at the end, this has to be the question about replica symmetry in the bulk, right? Because if it is symmetric, then this picture will follow. This picture will follow. I don't quite know how exactly this is happening, but you can use some dimensional arguments to say that there is no extra factor that you can, there's no extra term that you can write down there. Yes, I was just about to show that. So do I have how much longer should I continue? 5 minutes?
No.
Up to 5. Okay. Okay, fine. So
what exactly you mean by smooth or not smooth? What is it that you want to do?
Yeah. Yeah, I think the question for me is the status of this assumption, whether the bulk geometry dual to this replicated manifold preserves replica symmetry or not. Because if it does, then this picture has to emerge. So this we state as explicitly as an assumption about replica symmetry. Now you can ask a detailed question about what exactly is happening here. In case it is true, what exactly is happening here? That you can do. So in the end, going to one limit, you can calculate it. We did that for CFT2. Okay, I'll just go ahead and describe what happens. So here you get this conical angle of 2 pi by n. Here you get 2 pi by n and 2 pi by n. Now, more generally, what will happen is the following. So now let me look at this from above. So you have 1, 2, 3, and here there is sigma 1, sigma 2, and sigma 3, and you're getting a junction of this type, right? So the conical angle here, so the group elements that are associated to each vertex, meaning the group elements which are invariant under this vertex is going to be invariant under sigma 1 inverse sigma 2, right? This vertex is going to be invariant under sigma 2 inverse sigma 3, and this vertex is going to be invariant under sigma 3 inverse sigma 1, or rather the group generated by these guys. Okay, these guys. So this full locus is going to be invariant under that. So the conical angle that you're going to get here in general is going to depend on the order of this element, which in this case was n, but more generally it would be some order of this element. Okay, so now this tells us what we need to do to get a probe measure. We need to define sigma I as some function of n such that sigma I inverse sigma j. So for higher points, yes, this similar type of analysis will show you the picture that you get is of some sort of a web like this. Okay, so in general, you will get these loci. There will be internal loci also, and those would have, so let's say sigma 1, sigma 2, sigma 3, sigma 4, sigma 5. So these loci, which are, let's say, which are between the region 5 and region 3, would have sigma 3 inverse sigma 5 as the element that fixes this locus. Okay, So all in all, in various phases, any locus of any type, locus that is fixed under any ij combination, any sigma inverse sigma j can appear. Okay, so if you want to require that you get a probe measure for every point, in all phases, then you should require that for all ij, sigma inverse sigma j, its order should be such that it goes to 1 as n goes to 1. That would be the general condition that you would get a probe measure, right? Because once this goes to 1, the singularity associated to each of these lines would flatten out and give you a very light brane. Guaranteed? What is guaranteed? No, but you have to find now a sigma. There is no n to begin with, right? I mean, you have to find sigma i's which belong to a certain family labeled by n, such that sigma inverse sigma j, its order goes to 1 as n goes to 1. So in this case, for example, in the entanglement negativity case, in this case, for example,
you want sigma j to be something proportional to
n minus 1.
Order should go to O n minus.
Oh, sorry. Yeah, order should be. Yeah, order.
That's what. So it shouldn't be like that. That's what you want.
Yeah. So in fact, you can see this from here. The entanglement negativity, you have one G and G inverse, right? So this G is some generator of Zn, right? So now if you compute sigma inverse sigma j, those are G, G inverse, and G squared. There will be a G square also, which is sigma 3 inverse sigma 2, right? There will be a G square. So now, because G is an element of Zn, its order indeed goes to 1 as n goes to 1. Same is G inverse, but G square depends now on n, whether n is even or odd. In the case where n is even, the order of G square is n by 2. So in the n going to 1 limit, it will go to half. But in the n even odd case, the order of G square is now also n. So in that case, as n goes to 1, this will go to 1. Well, the idea is that you are computing these quantities, even the quantities with singularity, as a function of n, and you are taking the limit of those quantities. Yeah. No, this was just, I'm just giving an example where this is not hold. This does not hold. Right?
It does not hold.
Yeah, that's what you wanted, right?
I see. No, that's not what I wanted. But so just to understand, it's entanglement negativity, you're saying this prediction will not hold
for general n. Yeah. So you have to ensure that this holds. Now, in general, this is difficult to achieve. As Loga said at the beginning, this condition depends on the details of sigma, not just on the conjugacy class of sigma. But you can now simplify your life by assuming the following: the group generated by sigma I and the group generated by sigma j have only one as common. Okay, so that means they are kind of independent. The group generated by sigma I and the group generated by sigma j are independent Zn's, let's say Z1 and Zn1 and Zn2. Okay, in that case, the nice thing about this condition is that you can immediately write down the order of this guy in terms of the order of these guys. So let's say I always work with this condition now, that the group generated by sigma and sigma j are independent, and let's say the order of these guys is mi. So the order of sigma I is mi, let's say. Yeah. There are, well, for n odd, there is a holographic probe. I mean, if you analytically continue the n odd quantity, then in the n going to 1 limit, you can get to a holographic probe. Yeah, people usually don't study this because the main use of this entanglement negativity in terms of this partial positive partial transpose, it's nice. The even object is a nicer one. The odd object is not nice.
Sorry, but there are many papers on this entanglement negativity.
Yeah.
So what do they compute in the bulk?
I think this even object in the n going to 1 limit.
You don't see even or odd, right? You just see the n goes to 1 limit.
No. I mean, you have to say which quantity you are continuing, right?
So there's a continuation of the even quantity.
Yeah.
It reduces to some area.
With a heavy surface, not a probe. It's not a probe. But if you were to do for odd, for some reason, although it's not useful from a positive partial transpose point of view, as a probe of separability, let's say you still don't want to do that, then you will get a probe measure.
So these papers by Gautam and collaborators are somehow putting in odd.
Okay, those set of papers in particular, I don't know, but there's some other set of papers which do that. Okay, so now I will impose this condition so that I can calculate the order of sigma I, sigma j, and I will call the order of sigma I to be mi. Then this order is simply LCM of mi mj. Okay, just that. Now I want to solve a simple looking condition. I want these mi's to be some functions of n such that the LCM of mi mj should go to 1 as n goes to 1. Now what are the solutions to that? Now you can try to solve this condition. Now this condition, the solutions. So we found one solution in the beginning, which was to take mi is equal to n. Okay, if you take that, then sigma, this order is also n. The LCM of n comma n is just n. So now as n goes to 1, this whole thing goes to 1. Okay, so and then you can take.
Is this necessary, or is this something that you have used to?
I use this condition to simplify the analysis.
Without imposing this.
You could get solutions without imposing that odd entanglement negativity would be an example where this is not true, but you can still lead to a probe measure.
And there's just one annoying question. Is that there's this Carlson theorem kind of condition you
Yes.
need to.
Yes.
That's somehow being assumed here.
No. So that is a whole another discussion. So that's why I did not phrase it as some general analytic continuation for general states, because to do that you would need some Carlson theorem type condition. For this, I'm just interested in holographic states, let's say. For that, the analytic continuation is simply the continuation in the angle. It is the same type that works for the bipartite case. But now you can ask more generally whether this quantity that I'm defining in the n going to 1 limit is well defined for general class of states. That's a separate question, and a very turns out to be very intricate one. Okay, so anyway, so this is one solution to this. Another solution is the following: mi is equal to some ki to the power n minus 1. Okay, so because of this, if you use this LCM, that also gives you LCM of ki kj to the power n minus 1, right? So that in the n going to 1 limit goes to 1. Okay, so these were the two. This is the bigger class of conditions. Ki can be any positive integer. Exactly. Okay. So now. Okay, so now the singularity here, as we said, is 2 pi divided by the order of sigma I inverse sigma j, which in this case is LCM of ki kj to the power n minus 1. Right? In the n going to 1 limit, this becomes 2 pi, but entanglement entropy computes objects close to n going to 1 limit. So you can imagine what will show up is a log of LCM of ki kj. Okay, so that's what happens. What you get in the n going to 1 limit is a brane web where each segment, depending on what kind of segment it is, which sides it is separating, whether it's between, if it is between I and j, the segment, then it should have tension which is proportional to log of ki minus kj. Okay, in this set of solution, the coefficient is just 1. Okay, so this is what we call the multi-entropy. But in this more general class of solutions, you can have brane web of varying tension, where the brane segments have different type of tension. So here the assumptions. So one important assumption that went into this is the assumption of replica symmetry. I think if you assume replica symmetry, then this this construction will give you exactly the probe measure of entanglement that one needed. So now one can talk about the status of that assumption. Okay, so I will try to finish soon and just discuss what is known about replica symmetry. So first of all, one thing I should make clear is that even though all these pictures that I drew was for two-dimensional case, this is true for a general dimensional case. Okay, in general dimensions also you will have brain webs. There will be higher dimensional brain webs, or always co-dimension 2 brain webs. And now because they need to satisfy gravitational solution, you have to minimize the area of those. Okay, and in this case it will be a weighted area, weighted by log of ki kj, LCM of ki kj. Okay. Is the tension of that? Yeah, exactly. Yeah, and interestingly, for any set of k1, k2, k3, these things, LCM of log of LCM of k1, k2, k2, k3, and k3, k1, these three numbers always satisfy triangle inequality, which is necessary for force balance. This is just some interesting thing. Okay. Anyways, so you have this now.
That's probably just.
It's a very simple thing about LCMs. Yeah.
I'm just saying that's probably true just because of all the molecular similarity.
Yeah, maybe. I don't quite know what you're saying. But
I'm just saying that.
Okay, fine. So I just wanted to make this point that in higher dimension also a similar picture goes through. But now whether the replica symmetry is broken or not is a difficult question. It's difficult to analyze in higher dimensions. It's also difficult to analyze for 2 dimensions, which is perhaps the simplest non-trivial case. So what is known is only things about 2D. So in 2D, let's say q equal to 3, n equal to 2, it is known that this is the replica symmetry holds. The replica symmetry is preserved in the bulk. Okay, and I think this proof can be generalized to any value of q. This is something that I'm working on now. But what is known also is that for q equal to 3, n equal to 3, the replica symmetry is broken in 2 dimensions. Okay.
So what do you mean by that somehow there is no replica symmetry?
Yes. Yes, exactly.
Forbidden by some.
It is.
What is it forbidden by?
Singularity in the bulk. If you insist on replica symmetry, it produces singularity in the bulk.
Even in the before or.
Exactly. But for higher values of n, so this is for n equal to 3. What happens for n equal to 4 onwards? This is not known. So it could be that, let's say, for certain values, let's say even values of n, it is preserved. In that case, you would want to analytically continue the even values, skipping over the odd values, but it's just not known. So I think it's important to investigate this question.
If there's a singularity, it might just be that it is out like some.
Yeah, maybe. But also even if you compute the action for that singular solution, it's subleading compared to a solution that is replica symmetry breaking. So you want dominant solution.
There is a singularity which goes after you orbit.
Yeah, I'm not sure. At least in this case. So how can it go away after orbit?
Sometimes there are orbifold singularities and orbifolds of an orbifold is the original manifold, right? So I always thought in this argument, original manifold is what you want. Right? The orbifold is something. At least in the original.
Yeah, no, but nevertheless, even if somehow you can make sense of orbifolded geometry, then also it's nice.
It's always singular. Always a topic.
Oh, without that, right? I mean, modulo that thing. I don't want to call that a singularity. Because it's not quite a curvature singularity, it's just delta function there. As you approach it, you don't see it. Yeah, so yeah, I don't quite know. I don't quite know. I think this is important. This is a question that I'm currently looking at. In the case where one can do the analysis, what happens? So this is one thing. Here, where the replica symmetry is preserved. So that is, in this case, it is the boundary manifold is a sphere. Yes, but if you take higher values of Q, for which I'm saying that I think it should be preserved. For those cases, it will not be a sphere. Even then, it will be preserved. Here, the boundary manifold turns out to be a torus. That's what makes kind of analysis easy, because just a torus, not some crazy homogeneous surface. That's what I'm working on now, trying to see how exactly one can go towards answering this question. I think the way to do this is that you have to look at, okay, the boundary will be some higher genus surface, and the genus you can compute. And now you want to see whether the bulk which fills out this enjoys this replica symmetry, right? Now, in order to specify what is this bulk, assuming that it's a handle body solution, which itself I don't know whether it is or not, because there are non-handle body solutions also. Assuming it's handle body solution, it would be specified by a set of A cycles that are not intersecting with each other, right? Now you want to ask whether that set is closed under replica symmetry. So one can try to answer it that way. Just identify all the A cycles and the B cycles and how the replica symmetry acts on those cycles, and whether you can find a set which is closed in that manner. No, it depends also on N, not just on the, yeah, and not just on the surface, right? It also depends on how the replica symmetry is acting, because for various values of Q's and N, you can make it so that you get the same genus surface, but the replica symmetry may act differently. Yes.
So something based on those.
So what you're saying is that if I can find some energy surface, and if I can find the basis of A cycles,
Yes.
which are close to the replica symmetry,
Yes.
then the replica symmetry is not.
That tells you that there exists a solution.
But the handle body,
There exists, yeah, but whether it's dominant or not is again a different question. That also has to be understood. There exists a solution, non-singular solution.
non-singular replica.
Yeah, exactly. I think that will say. Okay. Okay, so I just wanted to say that about replica symmetry, and let me just end with some interesting properties that these measures have when you compute them for finite dimensional systems. So for finite dimensional system, as Surat was saying, the n going to one limit, the analytic continuation is a tricky thing. You know, you have to understand the boundedness of the measure, whether it fits in the Carlson criteria or not. So this is a bit of a tricky business. But what you can do is you can just study them for finite values of n is equal to 2, n is equal to 3, and so on. In general, these are difficult things to compute, but you can compute them on a computer. You can put it on a computer and compute. This is just a matter of let's say for n equals to 2, it's just matter of computing this contraction of rows, right? And this can be done with a computer. Let's say for qubit systems, for 3-party qubit systems, you can do that. And for qubits, you can push this all the way to n equal to 15 or so. It becomes it scales very badly with n, the complexity. But nevertheless, you can compute them. And also for certain class of states, you can compute this in closed form. For example, in W states, for W states, let me remind you what the W state is. It's some state A100. So this is some generalized W state. For these things also you can compute. Actually, it turns out to be a very nice calculation, because this calculation on some n by n lattice, it maps to a dimer model on the hexagonal lattice, where the on hexagonal lattice you have 3 types of bonds. Each dimer on each type takes the weight A, B, or C. And then this computation of the measure boils down to the calculation of the partition function on this hexagonal lattice. And this problem has been solved by Castell in particular. So that can be computed. Also for classical states, you can just think of 2 events with some probability distribution. For even such a simple thing, right? Just 2 coins and their probabilities when you toss them. Even for that, you can compute these objects n equal to 2, this types of object n equal to 3, and so on. And those are non-trivial objects. I have not seen any discussion of these things, what exactly they measure and so on. So I think it's quite interesting to even understand classically what they mean. But for classical states, you can again compute them. And they seem, all of them seem to enjoy the following property. So SQ, so let me call this object, the log of this object for Q part is SQ, and N is this, how many times this n by n grid, let's say. Sorry, I did not say how this looks like when, well, I did say it, but it was a bit implicit. But now let's say the Q is more than 3, for 4, etc. This will become a higher dimensional torus, because I had taken this condition where sigma and sigma j are independent with each other. So sigma acts only in this direction, sigma j acts in this direction. So all act in different dimensions. So as you increase the number of parties, you get basically a Q minus 1 dimensional torus. Some toric lattice, n by n toric lattice. I'm just discussing this case, mod sigma is equal to n, not this 2 to the n. In that case, the toric lattice will have different number, the size will be different. Okay. So in that case, the log of the partition function, I'm calling this, okay, with some prefactor. And it turns out that you always see that this holds. So by Q minus 1, I mean compute the same measure, but now you identify a pair of parties as a single party and compute a Q minus 1 type measure on that set, on that state. And always turns out that it is smaller than this quantity. So there's some sort of a monotonicity under coarse graining that is there for this measure. And the evidence is basically obtained by checking, first of all, numerically on many states, qubit states of this type, or some W state, and even holographically, I should say. You can see that the holographic states also satisfy this, even for general n. So as we said, in the n going to 1 limit is when this calculation simplifies, because the brains become very light. And when n is away from 1, these are heavy brains, so you don't know how to do the calculation because back reacts on the geometry. But nevertheless, even in the n integer case, away from 1 case, you can say something about it, right? Because if you have this, and let's say you now identify party 3 and party 5 as a single party, that amounts to not having a brain that separates these things. So you have to remove this brain. Okay, once you remove this brain, clearly the area of the remaining guy reduces. And not just this, it also adjusts itself again to reduce the area even further. So even for holographic states, it is clear that as you start identifying parties, this measure, even for finite n, not just in the probe brain case, even for finite n, you get a smaller quantity. So those states also seem to satisfy this inequality. So it would be nice to show that this inequality is true in general, but because the manipulation is of tensor type, analytic arguments so far are not working. So anyway, I just wanted to say this. This is also something that I'm currently working on. Okay, I will stop here. Thank you. Sorry for going over.
Are there any questions? If not, let's thank Abhijit.
Thank you.
Let me say what I want to say. I wanted to say that your CFT, you can calculate these objects, and those are computed by correlation of these operators. For large C, you can approximate this correlation function by this set of formulas. So this answer would be equal to free coefficient vertex times the number. It's a more long equation. That just maps to the y line. In that sense, this works for general. That serves as a check of this description. Modulo this